A very good morning. I bid to the Honorable Chairperson, panel members, ladies and gentlemen. Today I'll be sharing with all of you regarding my research that is very significant to the Royal Malaysian Air Force, which is the Aircraft Structure Integrity Program for C-130 aircrafts of Royal Malaysian Air Force. To make this presentation much more interesting, I have set my presentation contents here as a guidelines for all of us. At the end of my presentation, I would open to the floor for a question and answer session. Ladies and gentlemen, airframe structure are the primary system that is required to be attended for structural integrity. Widespread fatigue damage in a structure which occurs due to simultaneous presence of cracks at multiple areas will reduce the operational life on an aircraft. Through the implementation of fatigue life assessment, it is possible to determine if the structure of the aircraft is airworthy and safe. As a matter of fact, on 19th of December 2005, an amphibious aircraft, Ocean Airways Flight 101, crashed at Port Miami, killing 29 people on board. Multiple fatigue damage occurring at the right wing has reduced the fatigue life of the structure and caused this incident. Aircraft in the commercial world or with the military reach a stage after certain years of operation which is called structure fatigue. Structure reliability is affected by two most common factors, which are fatigue and corrosion. The period when the structure of an aircraft has reached its critical fatigue life is very much difficult to determine since it is induced by continuous cyclic loading. The airframe fatigue design principles are divided into two, which is the safe life and damage tolerance. Fatigue is the effect resulting from a component being repeatedly loaded. Failures happen due to the natural characteristic of the material or a damage that is subjected upon the material due to manufacturing or in-service process. It is subjected due to, first, mechanically or thermally induced loading, second, environmental effects to component, third, material characteristics, and fourth, continuous loading. In this study, I will focus on the transport fleet and specifically to the C-130, which are known as the workhorse or the backbone of the RMAF. The Lockheed C-130 Hercules, or also known as the C-130H, is a four-engine turboprop military transport aircraft originally built by Lockheed Martin. This image here depicts the C-130 aircraft, which is in the inventory of the RMAF. Safety is the major concern for all aircraft-related subjects, starting from the design stage till its entire duration of service life. Structural fatigue aircraft can significantly reduce its overall performance. Due to this alarming issue, the need for a thorough study is critical in order to determine the impact of structural fatigue on C-130 aircrafts in the RMAF fleet. This research will provide the platform for the structural life extension of the C-130. Besides that, it will also enable us to estimate the remaining fatigue life of the structure. Furthermore, the method used for structural life extension is being established and is capable to be utilized on other aircraft fleet. Finally, this concept also has its commercialization value. A field experiment method was used to address the operational framework for this research and was divided into three phases. Phase 1 of this study detailed out the critical location and the contributing factors. Besides that, the review of past study will provide information on critical locations of similar type of aircrafts from other operators since the critical location varies for each type of aircraft. Moving on to phase 2 of this study, in which the analysis of the critical location, which was identified earlier, was performed. There are a total of 5 major groups in the C-130 structure. They are then further analyzed based on individual aircraft to determine its specific critical point. To determine the fatigue critical location, a review on the aircraft structural historical data was performed plus aided with the non-destructive test. And in the third phase of this study, it will be the development of the aircraft structure integrity program. Stated here are the parameters for my study. They are divided into three factors. First is cracks by area, second is cracks by structural location, and third is types of mission flown by these aircrafts. Based on the structural condition analysis done using NDT or historical data, a total of 378 cracks were uncovered from all the 4 aircrafts, with the highest number recorded from aircraft Mike 3005. The result here indicates the analysis based on structural area and is divided by aircraft tail number. As I mentioned earlier, these areas are the 5 main group on a C-130 aircraft. The results here indicates that the nacelle area on all 4 aircrafts have recorded the lowest amount of cracks. Besides that, landing gear and wing group recorded higher number of cracks. This is most likely due to high concentration of loads at these locations. The landing gear is the most common area prone to cracks since it is subjected to continuous impact loading during landing and taxiing. The center wing box, being the critical location at the wing area, is also subjected to loads such as bending and tension. Fuselage and tail group are subjected to loads such as aerodynamics due to airflow. Crack mapping not only provides us with crack area but also its fatigue critical location, or FCL. FCL is defined as the structural area that is vital for the aircraft to maintain its structural integrity. These areas are commonly subjected to various kinds of loads. The OEM has provided a 33 reference point on any RMAF C-130 aircraft. They are categorized based on 4 main locations. Based on the data collected, the matching critical location for the studied aircraft falls at the fuselage area. Through the years since 2014 till 2018, RMAF has spent nearly a total of 570.61 million ringgit for structural repairs on C-130. However, since 2019, which marks the initial investment into the ASI program, it is forecasted that the operational expenditure for RMAF on C-130 structural repair will decrease with a total savings of nearly 36 million ringgit in 3 years. Aircraft Structure Integrity Program, or ASIP, is a systematic procedure applied to a particular airplane system to predict operational life expectancy of the airframe. The current scope of ASIP implemented in the RMAF has 4 main areas that will monitor the structure integrity. They are the usage monitoring, condition monitoring, fatigue monitoring, and environmental degradation management. The C-130 gives the RMAF a significant and viable long-term option for strategic and tactical delivery for joint and multinational operations. Extending the service life of the aircraft will result in a better return on investment. Broadly, the service can follow the 6 recommendations to manage its aircraft fleet's capabilities over the next 20 years. Since the aircraft has moved into the aging phase, the current scope of analysis should be expanded to determine the crack growth behavior. In this research, it is shown that the main reason for aircraft structural failure is fatigue failure by fatigue crack propagation. Hence, installation of humps will be very useful. Even though there were 378 cracks, however, all cracks or structural damage has been repaired and classified as standard repair. Usage and condition monitoring data are vital towards the development and sustainment of ASIP, which will allow us to carry out the Structure Service Life Extension Program. These are some of the key references used in this research. Ladies and gentlemen, with that, I end my presentation for today and I open the floor for a question and answer session. Thank you.